Welcome to this presentation, where we will look at 2D elemental mapping using X-ray fluorescence. The XRF spectrometer used was an EDXRF PC as shown. X-ray fluorescence occurs when an incoming primary X-ray strikes an inner electron of an atom and dislodges it from the atom. To correct the atom's instability, this vacant hole is rapidly filled with an electron from a higher orbit, and within the process, secondary characteristic X-rays are emitted. Every element in the periodic table has unique and strictly defined X-ray lines. Accelerating electrons in scanning electron microscopes can also be used to create the same characteristic X-rays by a similar mechanism as described above. This is scanning electron microscope electron dispersive X-rays. X-ray penetration depth and interaction with atoms to create fluorescent X-rays in material is superior to SEM EDX. Penetration depth depends on elemental density. EDXRF, or electron dispersive X-ray fluorescence, as it should be described, has detection levels of parts per million, whereas SEM EDX has typical detection levels of 0.1%. Penetration depth for elemental analysis from many hundreds of microns to several centimeters can be achieved using 10 kV to 50 kV X-ray tube energy and tube current up to 900 microamps. XRF EDX mapping can better detail homogeneity or inhomogeneity in samples. Large bulky samples can be placed in the chamber and analysed. Samples can be either under vacuum or at atmosphere for analysis. 2D maps can be displayed as region of X-ray intensity or weight percent. Samples require minimal or no preparation for analysis. Samples do not require conductive coatings. Effective 1D mapping is also available. XRF EDX analysis is limited to the sodium element onwards in terms of elemental analysis, although some of the latest XRF spectrometers now have the capability to analyze from carbon onwards. There are limitations on the size of the area to be analysed, based on the 30 micron spot size of the X-ray instrument itself. The sample analysed was a welded A335 P92 steel sample. The exact location is at the well-bulk interface as shown in the left image. The right image was taken with a stereo microscope to show better surface detail. Please note that carbon and nitrogen cannot be mapped with most XRF spectrometers. In the tables are the setting and parameters for the XRF mapping. The 35 kV tube voltage allows good X-ray penetration. The tube current guarantees healthy X-ray counts per second. The map pixels and size give good morphological feature detail. Please note that the original map ran for 43 hours for a weight percent map. The maps in this presentation are reprocessed for X-ray intensity. Maps can also be run for atomic percent. Shown is a grayscale image of the analysis map area taken from the XRF spectrometer. Since iron is the bulk element, the X-ray count intensity is considerable. At the interface between the weld and the bulk area, there is a high intensity region of iron. Chromium is the highest quantity in the list of minor alloying elements. Chromium is slightly depleted in the weld-bulk interface. The weld area shows what looks like some ordered structured distribution of chromium, while the bulk has a more homogenized distribution of chromium. The distribution of manganese shows stark difference between the weld and bulk regions. A higher concentration of manganese is in the weld region. With vanadium, the quantity is sparse in the weld region when compared to the bulk region. Nickel is relatively homogeneous across the whole sample, with some slight cluster features shown. Sulfur is also generally homogeneous across the sample. It is important to note that the sulfur K alpha X-ray line and molybdenum L alpha X-ray line are very close to each other and can be difficult to discriminate. The molybdenum L-alpha X-ray line map is pretty similar to the previous sulfur K-alpha X-ray line map. We can use the molybdenum K-alpha X-ray line to map for molybdenum, which is shown as evenly distributed across the sample. Niobium has some subtle features across the weld bulk region. Silicon clusters are shown in the bulk region, while silicon is greater in quantity in the weld region. Aluminium is generally homogeneous across the weld bulk region, but saying that, there are some clusters of concentrated aluminium. And finally, phosphorus, which is also homogeneous across the weld bulk region. To get an appreciation of sample penetration by the X-rays, we can estimate this from the tube energy used and the density of the majority element iron. Because the sample is a steel alloy, it is reasonable to say that penetration is approximately around 1000 microns or 1 millimeter. Therefore, the volume morphology is more detailed and provides better materials characterization data. An added bonus when using this mapping technique is that Compton X-rays are also counted. These particular X-rays are useful because they give an indication of relative material density and show features such as precipitates, voids, layers, volume defects such as cracks. In the case of the CPU sample shown, the electrical contacts are clearly defined within the processor. In this slide, we can see the power of deep penetration analysis of a nickel, chromium, cobalt, titanium alloy. It gives us a more 3D visualization of the bulk volume and greatly helps us in characterizing the sample. Element mapping by weight percent is shown in this metal shaving of bell bronze, with a thickness of approximately 414 microns. The map follows the surface contours of the bell bronze sample and reveals differences of thickness within the shaving sample itself. Bell bronze from the 18th century has a standard elemental composition of 78% copper and 22% tin, and this is reflected in the quantitative results, which are fairly close to this standard. One can appreciate that those who cast the bell 3 centuries ago were very skilled and knowledgeable in metallurgy. Final comment. With respect to characterizing sample morphology and element distribution, XRF EDX 2D mapping is a gateway to this process. What the end user gets from this is a reliable, low-cost, rapid, efficient, little or no sample preparation starting point for sample analysis. This analysis technique may eliminate the need to use expensive and time-consuming methods, such as, for example, plasma-focused ion beam scanning electron microscopy. XRF EDX 2D mapping may be a precursor technique that may complement other more advanced material characterization techniques, such as the example given. The end. Thank you for your time and patience. Comments or questions are welcome.